everybody. In this session, we will discuss concepts about work, energy, and power. Let us enter into. This lesson contains concepts of work, energy, work energy theorem, law of conservation of energy and its applications, collisions. We will see one by one. Work. Work is the product of force and displacement in the same direction. So for that, Fs cos theta is also needed. Theta is the angle between force and the displacement. Remember, if both are in the same direction, then Fs will come, that is the maximum work. If both are in perpendicular direction, then the work will not be related to that force. So work done by that force is 0. Okay, next. Maximum work, minimum work, and negative work, positive work are as follows. If the angle between the force and the displacement is obtuse, then negative work will come. And maximum work will be when angle between them is 0 degrees or 180 degrees in magnitude. You are going to get work maximum. And here, work is a scalar quantity whose units are joule. Right? Suppose the displacement is given in the vector form like r1 bar is initial position and r2 bar is the final position, then you can have f bar dot s bar. F bar dot s bar will give you work done. Okay. Here a small change I would like to make, that is f bar dot r bar. This is f bar dot r. Yeah, okay, f bar dot r bar. Dot product is a commutative. So r bar dot f bar or f bar dot r bar, both are same only. Next, area under force and displacement graph gives work done by that force during that displacement interval. Next one, work done by a constant force is Fs. So this is the graph, and that you are going to have, right? F bar dot s bar indicates Fs cos theta. Okay. If the force is not constant, then you need to go for integration. That's what I want to discuss here. Okay. Next, work done by a variable force. Work done by a variable force is integral of f dot dr. Integral of f dot dr. If it is a variable force, you need to integrate. If it is a constant force, you can direct multiply. Okay, next. Body of mass m is lifted from ground to a height h by using a minimum force F, then minimum work done by the force in lifting is Fh cos 0. Work done by lifting force is Fh cos 0. Lifting force is upwards. Let me take up another color. Lifting force is upwards, displacement upwards, so that's why cos 0 comes here. Okay, work done by gravity, gravitational force downwards, displacement h upwards, so we need to take cos 180 degrees. So negative work done by gravity, positive work by the lifting force. Okay, next. Suppose a body is lifted up, then work done by the tension, net acceleration m, force is net acceleration you have to consider, force, net acceleration you have to consider mg plus a into h, mg minus a into h for sliding body and for lifted body. Next, work done by friction. A body moves with uniform acceleration when the work done by the force is, see, the body is moving with acceleration a, it is experiencing friction f, then applied force must balance friction and to give acceleration. So its work done will be F plus ma is the total force into displacement. So that is the logic here. Next, a body of mass m and density d lies on a non-viscous liquid of density d2, then minimum work done in lifting the body in that particular liquid with uniform velocity is given by mgh of 1 minus d2 by d1, density of liquid by density of the body. That is nothing but effective gravity you are taking. Effective gravity g dash is equal to, we suppose in a fluid, effective gravity g dash is equal to g into 1 minus dl by dv. That concept only we are using. dl means density of the fluid, db means density of the body. And a bucket full of water of mass m is lifted with uniform velocity. That means minimum force is needed for that. In that case, work done in lifting that bucket is lifted by L, but whereas the rope is lifted by L by 2. So mgl is the work done against bucket, and mgl by 2 is work done against the rope, because rope's mass lies at the center of mass. That is the reason. Next, a pendulum of length L, mass m, the bob is pulled aside through an angle theta with the lower vertical by a horizontal force F. That means it is pulled aside like this. Then work done by force, work done by gravity, all those expressions I would like to give. Work done by the gravitational force is negative because body is lifted up, gravitational force downward. So mgl of 1 minus cos theta. Work done by the horizontal force, Fl sin theta, force and the horizontal displacement. Horizontal displacement is L sin theta, Fl sin theta. Uniform rod of mass m and length L is suspended vertically. Rod, not pendulum. Then rod's center of mass lies at the center of the rod. Then effective length will be L by 2. So the same formula will come, but mg L by 2 of 1 minus cos theta you have to take. mg L by 2 of 1 minus cos theta. I repeat, suppose it's a pendulum, its length you have to consider this one, L. If it is a pendulum. If it is a rod, then you have to consider, if it is a rod, its mass is concentrated here. So this one only you have to consider, L by 2 only you have to consider. Okay, with that only the things will come, because mass is raised. So center of mass rise you need to consider. Next. Ladder thing. Work done by the gravitational force minus mgh when a ladder is raised to a height h, then center of mass position change only you have to consider, because it's a uniformly distributed body, that's why. And where h is the height of center of gravity, that is equal to L by 2 sin theta. So h is equal to L by 2 sin theta, opposite side, right, in the picture. So work done by gravity is mg L by 2 sin theta. That is not 1, that is L by 2. This is L by 2. L by 2 sin theta. Next. May I give with another color so that it will be good to look and you will identify. Of course, in a printed material it's correct only. Just in this, some symbols will take up a different font. That's why it came like that. mg L by 2 sin theta. Yes. Next. Uniform chain of mass m, change of potential energy is the work done. You can think like that, so it will be better and easy. Change of potential energy. You know, potential energy initially here. If on hooking the same chain to itself, then potential energy comes to this level. So what is the height difference? You can think the height difference is h is equal to L by 4, right? So change of potential energy will be the work done. Change of potential energy will be the work done. Yes. So mg L by 4. Directly you can think. Change in potential energy is mg L by 4. So the body is lifted. Initially the body, this is initial position. This is final position. So initial position to final position, mass is raised. You can feel like that. So mgh. H is L by 4. So hanging the rope to itself or the chain to itself, then work done is equal to mg L by 4. Work done by gravity minus mg L by 4. Work done by the man plus mg L by 4. That is the thing. Next. Uniform chain of mass m and length L rests on a table. Uniform chain of mass m and length L rests on a table. Okay. Suppose 1 by nth part of the chain is hanging and it is pulled onto the table, then work done is equal to m by n, because total mass you shouldn't consider. Hanging part mass only you have to consider. Hanging part mass is m by n, because 1 by nth part is hanging. 1 by n into gh. H will be L by 2n. Why, sir? Why, sir? Suppose this is the chain. Suppose this is the chain. Okay. This length is hanging. Suppose. See, this length is L by n. L by n is hanging. But its mass will be concentrated here. So, half of that you have to take. So, mass initially hanging here, finally here, because it's pulled onto the table. Finally here. This is final, this is initial. So, height difference is L by 2n. So, that's what here I indicated, L by 2n. So, mass is raised through L by 2n height. How much mass? M by n only, not the whole mass. So, these things are typical things you need to concentrate more. So, work done is equal to mgl by 2n square, mgl by 2n square, mgl by 2n square. Next, a uniform chain of mass m and length L rests on a smooth horizontal table. A uniform chain of mass m, length L resting on a smooth horizontal table. If it is raised in such a way that first initially 1 by n1 is hanging, finally 1 by n2 is hanging, then the work done is mgl by 2 of 1 by n1 square minus 1 by n2 square. Similar procedure. Okay. Next. Suppose a block, a body of mass m is on a smooth inclined plane of inclination theta. Okay. And then length of the plank is L. Length of the plank is L. Work done by the gravitational force in pulling the block down. Work done by the gravitational force in pulling the block down is, remember, if you want to take W sin theta, then take length L. If you want to take W, then take height. So, this is like if you write a letter to the principal, then post to the principal only. If you wrote a letter to your mom, then post to your mom only. Don't post in a different way. That means if you are thinking about this displacement, then this force you have to think. If you are thinking about this displacement, this force you think. Or if you are thinking about this displacement, then you have to think about this force W sin theta. So whatever the respective thing. So mg sin theta into L, mg sin theta into L, and mg sin theta, okay, if it is friction is there, then mu mg cos theta into L will come against friction. So this is L, not 1. The remaining things are as usual. Next, net work done by the resultant force if it is moving with what you call frictional force as well as applied force, both. Then mg sin theta minus mu k mg cos theta into L. That is the net work done on dragging a body by the gravity from that surface, that position to the ground. Next, total work done by a gas during the change in its volume. See, work done by the gas on expanding itself from V1 to V2, that is work done is equal to pressure at which it expands into volume change. So this formula will help you even in thermodynamics. Work done is equal to pressure into change in volume, P into V2 minus V1. Work done by the force of gravity in equalizing the levels of this picture. You need to observe the picture. Here different levels of the liquid is there. One is up to H1, other one is up to H2. Then equalizing this, work has to be done by the gravity, that is given by work done is equal to Pg, not Pg, that's actually rho g, density rho g into H1 minus H2 by 2 whole square. Rho g into H1 minus H2 by 2 whole square. That is the work done in equalizing the liquid. Next, here n blocks are there on the table whose masses are m each, and what is the side A. Then difference in potential energy you keep in mind, so that work done in arranging them one over the other you will get. Work done in arranging them one over the other you will get by taking difference in potential energy. So initial potential energy mg a by 2, because at the center potential energy lies, mg a by 2. How many are there? N are there. So n mg a by 2. Potential energy when the blocks are piled to form a single column, then potential energy will be nmg, total mass into gravity, into total height is na by 2. So na by 2, n square mg a by 2 will be the potential energy of the final system. So initial system, final system difference you will get the work done by the gravity in arranging them against the gravity. It's because you are showing positive. If you are showing positive, that is against the gravity. mga by 2 n into n minus 1. n into n minus 1 by 2 mga. Like that you can memorize. Next, work done by the spring force. Work done by the spring force in stretching from x1 to x2 or x initial to x final, that is work done by the spring force. See, work done by the spring force is x initial square minus x final square. Work done by us, final minus initial. That is the difference. Okay. Next, when the body moves in the direction, when a body moves in a circle, work done by the centripetal force is given by 0. The reason is work done by centripetal force and the displacement are perpendicular. I repeat, this is the displacement, ds. This is the force, centripetal force. Centripetal force always perpendicular. So obviously, yes, work done by centripetal force is 0. Work done by centripetal force always 0. Obviously, the kinetic energy is maintained constant, and the kinetic energy expression is half mv square and can be also be noted as p square by 2m, where p is the linear momentum. Work energy theorem. The sum of, a very important point it is, even many theoretical questions also came earlier. The sum of work done by all the forces, including internal and external forces acting on a particle or a system, is equal to the change in its kinetic energy, irrespective of the type of the forces. See, law of conservation of energy is not applicable for all the kinds of forces. It is applicable for only conservative forces, and that too internal forces should do work and external forces shouldn't do any work. But here there are no conditions. There are no such conditions. That is, sum of all the forces that are acting on a system causes change in kinetic energy, including internal forces, external forces, and everything. Next, while applying work energy theorem, one must take into account not only the external but also internal forces to calculate work done. Remember, that's important. Next, conservative, non-conservative, both are applicable. Conservative force. If the total work done by a force in a closed path is 0, then that force is known as conservative. If the total work done is not 0, that is non-conservative. Then work done by a conservative force in moving a body from position initial to final is independent of the path. In any path you can, if conservative force is doing work from A to B, in any path you can go, work done will be same, if it is a conservative, right? Next, for conservative forces, that what you call del cross F is equal to 0. Del cross F is equal to 0. Simply del cross F is better. Del cross F, that is equal to 0. Non-conservative force. If work done by the force, around a closed path is not equal to 0 and it is independent on the path. So no, it is dependent on the path because it's non-conservative force. Non-conservative force is dependent on paths. Such a force is called non-conservative force. Frictional force, viscous force, work done by the non-conservative force will not be stored in the form of potential energy. Non-conservative force work done will not be stored in the form of potential energy. Next, it is path dependent, that is path independent. Okay, next. Equilibrium. Usually equilibrium means people are having one kind of misconcept in their mind, that is, equilibrium means people will feel their body is at rest. That's not certainly. Of course, partially it is true. Body at rest is in equilibrium, no doubt. But bodies moving with uniform velocity are also in equilibrium. Yes, that also you have to put in your mind. Acceleration zero systems are in equilibrium. Here it's a different thing we are discussing, that is status of the bodies. That is, for the equilibrium of a body, the net force and net torque on it must be 0. Such things are known as equilibrium states. So F external force is equal to minus du by dx, or derivative with respect to the position of potential energy is 0, then we can say that the system is in equilibrium. Yes, stable equilibrium. Du by dx equal to 0, d square u by dx square is positive and potential energy minimum. Such state is known as stable equilibrium. On disturbing it, again it comes back to the same situation, that is stable equilibrium. Potential energy minimum. Next, unstable equilibrium. The conditions are reverse. Du by dx is equal to 0 and d square u by dx square is equal to negative and potential energy maximum. In that cases, unstable equilibrium. Neutral equilibrium. Du by dx 0, d square u by dx square is 0 and Pe remains constant in all the positions, that is neutral equilibrium. Next, potential energy and equilibrium in the figure. For detailed lectures, you need to observe our lesson lectures. Okay, this is a brief review. Potential energy and equilibrium in the given figure. Potential energy, equilibrium. A position is which type of equilibrium? A position is d square u by dx square positive and having minimum potential energy, stable equilibrium. And B will be maximum potential energy and unstable equilibrium. Yeah, d square u by dx square is negative in this case. Next, potential energy curve. Yes, grade U. Del operator. Del operator. Yeah, conservative force is defined as negative gradient of potential energy. Conservative force is defined as the negative gradient of potential energy. Conservative force is defined as negative gradient of potential energy. This sentence is important. F conservative is equal to minus grade U. Grade means del operator. Del operator is I into dou by dou x, j into dou by dou y, and k into dou by dou z. Into that U you have to take. Next, scalar potential energy function, we also call it as. Next, gravitational potential energy. The change in the potential energy of the system corresponding to a conservative internal force is potential energy final minus potential energy initial, that is equal to integral F conservative into dx. That is what you call gravitational potential energy, work done by the internal conservative force on the system. Gravitational potential energy near the earth surface. Gravitational potential energy near the earth surface. Near the earth surface, this is actually potential energy difference, work done by the gravity in lifting a body through h is mgh. This is actually potential energy difference from surface to a particular height. From A to B, potential energy difference is work done by the gravity. Difference of work done will be change in potential energy. Work done is equal to change in potential energy. Spring potential energy U is equal to half kx square. X is the elongation. Next, mechanical energy. Total mechanical energy is nothing but here in this case kinetic energy plus potential energy. E is equal to k plus U. This is total mechanical energy. When no external force acts on the system and all working internal forces are conservative, then total energy of the system remains constant, which is known as law of conservation of energy. Power. The time rate of doing work is called the power delivered by the force. The time rate of doing work is called the power delivered by the force. So P is equal to dW by dt. Don't learn power is equal to W by T. Learn power is equal to dW by dt. Rate of doing work is called power. So for constant force, F into V you can take as power for constant forces only, not for variable forces. This has a condition. Why are you doing F dot V only V is integrated, F dot S where only S is integrated? That means F is constant here, so S is differentiated, you can feel. I repeat, power is equal to work done by time d by dt into work done is equal to Fs if you take, then why are you taking F dot ds by dt? Because I'm feeling that F is constant. Whenever F is constant, then only you can take like this, isn't it? So for that case only F into V will come. Otherwise F into V won't come. So F constant, then F into V you can take. Otherwise you shouldn't take. Next, average power is equal to work done by the force in a given interval by time interval. This is average work done. Instantaneous, obviously dw by dt is for small time interval, and any kind of work done you can take on the numerator, time taken during that will be in the denominator, will give you rate of doing work, that is nothing but par. Next, par can be positive, negative, 0 also. Par can be, but remember many times students are confusing whether we are asking par or work done. We are asking par comparison or work done comparison. Work done is different, par is different. Don't confuse with them. They are different things. Slope of the graph work time dw by dt will give you tan theta, that is nothing but instantaneous par. And a machine gun fires n bullets each of mass m with velocity v, then kinetic energy imparted to each bullet is half mv square, and n bullets, n into half mv square is the total work done by the gun by time, will give you power of the gun. So a gravel is dropped onto a conveyor belt with which is maintaining the velocity v, and the gravel is falling on it at the rate of dm by dt, then power required to maintain that velocity is dm by dt into v square, because dm by dt into v is the force, into v will give you power. And power of the motor that is delivering liquid, need not be water, any fluid, velocity v through a pipe of cross section a, then power is equal to half a rho v cube. Rho is the density of the fluid. If it is water, water density. It is applicable for any fluid, okay, not only for water. Next, area under power versus time graph. Area always is the product, power into time. Power into time is work done. Power by time, nothing, no significance in this case. Next, efficiency of a crane or motor. The ratio of output power by input power is called efficiency. If you multiply with 100 in percentage, you are going to get. This is efficiency. Here actually it should be like this. Eta is equal to power output by power input into 100. Equal to should be in between, okay, that you can understand. Next, motion in a vertical circle with uniform speed, vertical circular motion. A particle of mass m is rotated at uniform speed v in a vertical circle of radius r with the help of a light string. Then the sum of its kinetic energy and potential energy is not constant. Sum of Ke and Pe is not constant. A particle of mass m is rotated with uniform speed v. If it is rotated with uniform speed v, that means you are applying external force. Otherwise, how can it maintain the same speed? That's why Ke, Pe not constant. Remember that. Next, and tension at the lowest position is half mv square by r plus mg. Tension at the highest position is half mv square by r minus mg. And tension at any random position is mv square by r plus mg cos theta is tension at any random position. And v1 is the velocity at the lowest position, v2 is the velocity at the highest position. Difference of tension is 2 mg. And a vehicle of 6 mg is for only critical circle dear. This is for any circle, a different circle. A vehicle of mass m is traveling with uniform speed v along a concave road, and then a convex road of same radius of curvature r. Then r1 r2 are radii and normal reaction forces here, okay, at the lowest point of the concave road and the highest point of the convex road respectively. Then r1 is equal to mg plus mv square by r, and r2 is equal to mg minus mv square by r. Maximum speed of the vehicle at the highest point of convex shaped bridge, so that the vehicle does not leave the surface of the bridge when the velocity is root gr. This is nothing but for a critical circle topmost point's velocity, that is root gr. Such points only, these are all. Motorcycle and everything, whatever not leaving the contact means that is having a velocity root gr. That is the sense. A particle of mass m suspended by a thread is given by a horizontal speed u, radius r. Then speed v at any position is square root of u square minus 2gr of 1 minus cos theta, where u is the velocity at the lowest position. And at 180 degrees, square root of u square minus 4gr. And at velocity at point A, that is the lowest position, that is u only. And tension at any position is mv square by r plus mg cos theta, at any position tension. Next, tension at the lowest position is mv square by r plus mg. V is the velocity at the lowest position. At the highest position, mv square by r minus mg, and v is the velocity at that highest position. Next one, the difference between maximum and minimum tensions are Ta minus Tb is 6 mg in this case. Which case? Vertical circular motion with different velocity. Lowest position velocity is v1, highest position velocity is v2. If v1 and v2 are equal, then that is 2 mg. Here it is 6 mg. This is the difference between independent of velocity of projection, and this difference is independent of velocity of projection. That means for any what you call velocity of the circle, lowest position v1, final position v2, and no external force is acted, only gravity is acting. In that case only Ta minus Tb is equal to 6 mg. Other than gravity, no other force should act in it for the system. The critical condition means at the topmost point it should have root gr velocity. Tension must be 0 at the topmost point. Velocity root gr, lowest velocity root 5 gr, very good. And velocity at any position root 3 gr plus 2 gr of cos theta, or gr can be taken common, root over 3 plus 2 cos theta also you can tell. And tension at any position theta, 3 mg of 1 plus cos theta. Then next, V minimum is independent of mass of the body, and T minimum is in the string is independent of radius of the vertical circle. If velocity greater than or equal to root 5 gl, the bob describes a vertical circle. If it is lesser than root 2 gl, then the bob oscillates. Yes. And cos theta is equal to u square by 2 gl, and the height attains is u square by 2g. If the velocity is in between root 2 gl and root 5 gl, then the bob neither perform oscillatory motion nor the vertical circle. It will be rising to the second quadrant and will fall down. So its motion will be a disturbed one. And cos theta is equal to what height it can go? Cos theta equal to 2 gl minus u square by 3 gl, and the height at which the tension in the string becomes 0 is u square plus gl by 3z. It's a special case for it. Okay. Then next, collisions. We will discuss collisions now. Collisions we are going to discuss in a brief manner. That is, in all types of collisions, law of conservation of linear momentum is valid. And also, collision means the bodies need not come into physical contact, only change in linear momenta is expected. They need not come and touch. Yes, because alpha ray scattering experiment, alpha particle comes and hits the gold nucleus. It won't touch actually, it will try to touch and will come back, or it will be diverged out, isn't it? So in that case, we are going to say that even collision happens. Collision happens if there is a change in momenta. So whenever there is a change in momenta, we can say that there is a collision. So that should be kept in mind. There is no need of physical contact. Linear momentum always conserved in all the types of collisions. Next, Newton's third law is valid at collisions. Automatically, that is a consequence of linear momentum. Now, types of collisions are head-on, one-dimensional collision, and oblique collision. These two we are going to discuss in our sessions. Law of conservation of linear momentum is m1u1 plus m2u2, total momentum before collision, m1v1 plus m2v2, total momentum after collision, and energy is conserved only in case of elastic collision, that is kinetic energy before, that is equal to kinetic energy after. And for only conservation of energy and what you call elastic collisions, for elastic collisions, elastic one-dimensional collision, V1 is equal to m1 minus m2 by m1 plus m2 into u1, 2m2 by m1 plus m2 into u2. V2 is equal to 2m1 by m1 plus m2 into u1 plus m2 minus m1 by, not m1 minus m2, this is second one. So m2 minus m1 by m1 plus m2 into u2. I know this formula, you2 should practice. Next. This is relative velocity of separation is equal to relative velocity of approach for only one-dimensional head-on elastic collision. This happens. For other things, these two will not be equal. Next. Yeah, first m1 is equal to m2 is a special case. Two identical masses are going to collide elastically, then they exchange their velocities. Adla badli ho jate. The velocities will be exchanged. Your velocity will be to me, to my velocity will be to you. If we bombarded elastically, identical mass, see, masses must be identical. Next, if m2 is greater than m1 and m2 is at rest, it's another special case. m2 is greater than m1 and m2 is at rest, then m2 velocity no change, m1 will be reversed. It is like a ball bounced back from a wall. That is, m2 is heavy, so no change in m2 velocity. m1 will be reversed, so v1 is equal to minus u1. Similarly, suppose the second body is at rest and first body is hitting, then fractional kinetic energy retained by the first body is m1 minus m2 by m1 plus m2 whole square. Fractional kinetic energy transferred to the second body 4m1 m2 by m1 plus m2 whole square. This is fractional kinetic energy transferred, right? Next, quotient of restitution E is equal to relative velocity of separation after the collision by relative velocity of approach before the collision. That is coefficient of restitution, which decides the extent of collision, whether it is elastic, semi-elastic or inelastic. If it is elastic collision, E value will be 1. If it is inelastic collision, E value will be 0. If it is a semi-elastic, then E value lies in between 0 and 1. In that case, kinetic energy is not conserved. Only kinetic energy conserved in case E equal to 1. Okay, next. Here, suppose a bouncing ball falling from height h, then rises to a height hn in the nth bounce. That is, hn is equal to e power 2n into h. hn is equal to e power 2n into h. Velocity of the ball after nth bounce is vn is equal to en into v. Velocity after nth bounce is en into v. Next, the quotient, the total distance traveled by the ball before stopping when it is bouncing is h into 1 plus e square by 1 minus e square. Total time taken before stoppage is square root of 2h by g into 1 plus e by 1 minus e. Okay, these two are very frequently asked points. Okay, you need to have this average and all those things you can calculate using a total displacement by total time, total distance by total time, like that. Next, this is very, very important. Oblique collision. Whenever a body collides the floor obliquely with an angle of inclination alpha and bounced with velocity v at an angle beta, then the floor is exerting force in vertical direction. So vertical component is only going to change in velocity as well as in momentum, but not in horizontal direction. There is no force in horizontal direction. So horizontal directional velocity and momentum will be same. V sin beta is equal to u sin alpha, and V cos beta is going to change. So final V cos beta, final velocity is EU, that is EU cos alpha. See, final velocity is equal to E times of initial velocity. Whenever you are going to observe this type of things, other body is at rest, then happily you can take this. V final is equal to EU. Whenever other body is at rest, you can take this one. Next, final velocity is V cos beta, so initial velocity U cos alpha, hence this one come. And the velocity after bouncing V is given by U square root of cos square alpha plus E square sin square alpha. And this is important relation, tan beta equal to tan alpha by E. Final angle and initial angle relation, tan beta is equal to tan alpha by E. Next, For semi-elastic collisions, final velocity expression is m2 minus em1 by m1 plus m2 into u1, 1 plus e into m2 u2 by m1 plus m2. Similarly, the v2 also. Next, loss of kinetic energy from the system also I am going to give. Yeah, this is the expression. Half m1 m2 by m1 plus m2, this is called reduced mass. m1 m2 by m1 plus m2 is reduced mass. Half reduced mass into u1 minus u2 whole square 1 minus e square. This is the loss of kinetic energy from the system. You take initial kinetic energy, take final kinetic energy, subtract, and then you will get this expression. See, those derivation things you can do in leisure. A collision in which the two particles move together, this is an absolutely special case. A collision in which the two particles will move together after the collision, such a collision is completely inelastic collision. If they are moving separately, that is not inelastic collision. Then that common velocity is given by m1 u1 plus m2 u2 by m1 plus m2. Maximum energy is lost during complete inelastic collision, and that maximum energy loss is, yes, half m1 m2 by m1 plus m2 into u1 minus u2 whole square. This is maximum loss of kinetic energy. Next one is oblique collision stories only. Net impulse on both particles is zero during the collision. Net momentum of the both particles remains conserved before and after in any direction. Only one particular directional momentum only conserved. That only conservation you have to consider. But the entire thing at a time you shouldn't. That I'll show you in a different way. See, either horizontal directions before momentum, after momentum you can take, or vertical direction before momentum, after momentum you can take, or vector form of momentas can be conserved. That means if you are trying to equate total momentum before and after, total momentum before in one direction, in the same direction, total momentum after you have to take. That's what I want to say. Either that is vertical direction or horizontal direction, whatever you can take, that you can take. Or vector way you can take, that is automatically ij case will be there. So similar things you are going to equate, but never equate magnitude of momentum of one direction initial and final of another direction. You shouldn't equate. Okay, before collision, whatever the directional momenta is there, after collision that directional momenta you have to equate to have a conservation of law of conservation of linear momentum. Next, coefficient of restitution is v1 cos beta 1 minus v2 cos beta 2 by u1 cos theta 1 minus u2 cos theta 2. Next, this is the end of this work energy per concept session. We will do problems in the subsequent shows. Bye. Revise.